So when it comes to exponentials, there are a few patterns we can look for. There are a few things we want to keep in mind in terms of how they behave, most of which come down to what happens with that term b. So that's what we're going to pay close attention to here, where we have that the domain of f of x equals b raised to the power x is all real numbers, negative infinity to infinity, with the range from 0 to infinity excluding 0, because you can never raise something to a power and get 0. Their graphs all pass through the point 0, 1, because at 0 we get b raised to the power 0, which equals 1 for non-zero b, with y-intercept at 1, and because the range is from 0 to infinity, not including 0, the functions will not have an x-intercept. If b is greater than 1, then that function will have a graph that goes up to the right and is increasing, where the greater the value b is, the greater the rate of increase, because the value b determines that rate of increase. If b is between 0 and 1, then the function has a graph that goes down to the right and is decreasing, where the smaller the value of b is, the more it's going to decrease by, because again, that's the growth rate there, and that gives us towards something called exponential decay, which we'll see later. We have that f of x equals b to the x is 1 to 1 and has an inverse. It's a very special kind of function that we'll see in the next section. And the graph of f of x equals b to the x approaches but does not ever touch the x-axis. So the x-axis, or y equals 0, qualifies as a horizontal asymptote. And then from here, with these ideas in mind, we can also talk about how these functions interact with things like transformations, where we have that with a vertical translation, we are adding or subtracting a constant c to the function on the outside, which again pushes it up or down. Then for a horizontal translation, that means putting it into the exponent, which is going to move it left or right in exactly the way we'd expect. Then we get reflections, where negative bx reflects it around the x-axis, and b to the negative x, reflects it around the y-axis, as we saw in the last example. And then we have the vertical stretching and shrinking based on where you place the value c, either as a constant multiple on the outside or a constant multiple on the x, just like what we saw before, except with these we have our own very specific context for how it works. So, for a quick example of the way we can work with these, if we want to use the graph of f of x equals 3 raised to the power x to graph g of x equals 3 to the x minus 1, it's just a matter of knowing those transformations, where we have for f a graph something like this, which you should probably check for yourself just to be sure. Use some of those ideas we had last time, which we can translate 1 unit to the right, because we're subtracting 1, so just pull it over a little bit, and that gives us our graph of 3 to the x minus 1. Transformations are always kind of nice if we know what we're doing there in terms of being able to get from one to the next. And from here, we're going to finish the section with one of the classic applications of exponential functions, which leads towards the most important of the exponential functions in terms of a very special number called e.